Alright, I'd like to clarify some of the aspects of the Newton-Raphson explanation, which I wasn't particularly happy with. What we're trying to do is solve the blue and the red equation, and I said let's write the first one as f1 of x and y is x squared minus y equals 0, and the second one, function 2 of x and y, is 2x plus y minus 15 equals 0, and we know where one of the solutions is in reality, but let's say we don't and we guess that a solution is at 5, 5. So that's going to be our x bar, y bar, and in general x is going to be our starting point plus some delta, and y is going to be our guess plus some delta y. And the goal of Newton-Raphson is to approximate the two functions as lines and then to find the intersection of the lines. So we want to find a very specific delta x and delta y that's going to take us from our guess to the intersection of these two linear approximations. Now we said we'd use Taylor series approximations, which means f1 of xy is the function evaluated at our incorrect guess. That's going to give us some non-zero residual amount, plus x slope evaluated at the starting point times delta x plus y slope at the starting point times delta y. We plugged in a few numbers. We said that the x slope was 10 and the y slope was minus 1, and the residual was 20. So our first function approximation came out to be 20 plus 10 delta x minus delta y equals 0. So that's a line with a slope of 10 that passes through the blue curve at the point 5, 25. And the way I found this point at which I want to draw my line, I started at 5, 5, and I said if I just go straight up, in other words, if delta x is 0, then I'm going to get a delta y of 20. So I'll go up from my guess point by 20, and I will draw my line with a slope of 10. The other function, f2, it just so happens that my guess is on that function and it's linear. Anyway, f2 of xy is going to be 0, just by fluke, plus the x slope of the second function times delta x plus the y slope times delta y. This is what we got. And if I start at my guess and I want to go up to find the function, so if I start at 5, 5 and say delta x is 0, I don't need to go up at all to get to the function. I just stay where I am and I plot a line with a slope of minus 2. And that's the red line. So now the next step is I want to find delta x and delta y that take me from 5, 5 to whatever this intersection point is. So I'm going to do that on the next page. So I'm also going to write out the approximation of f2. So let me add another page in here. So we'll append a page, and we'll start writing out the approximations. I'm going to write them out actually in a column vector. So f1 of xy and f2 of xy, think of that as a vector of two functions, is going to be f1 at my guess and f2 at my guess plus, okay, the first function was f1 at the guess plus partial of f1 with respect to x evaluated at the guess multiplied by delta x plus the y slope of function 1, which was partial of f1 with respect to y, multiplied by delta y, again with this slope evaluated at the guess. f2 is going to be f2 at the initial guess plus an x slope evaluated at the guess times delta x plus a y slope times delta y. So here is what's called the Jacobian matrix, this matrix of slopes. Here is the function evaluated at our guess, which, unless we're extremely lucky, is going to be non-zero, and that non-zero value is called the residual. And if I want this to be 0, I'm going to have to find a very particular delta x and a very particular delta y. So if I set this to equal to 0, and if I solve for the delta x and delta y that makes this equal to 0, I'm finding the corrections to my initial guess that will give me the solution if those two functions were actually lines. So in this example, my residual of function 1 was 20. My residual of function 2 is 0. My Jacobian matrix, at 5, 5, the slopes were, let's see, what were the slopes? The slopes were 2x and minus 1. And for the second function, the slopes were 2 and 1. Okay, so my Jacobian matrix is going to have 2x minus 1, 2 and 1. Go back and double check that. Yes, 2 and 1. Good. Alright. Okay, so that's the residual vector plus the Jacobian matrix multiplied by delta x and delta y is equal to 0 for delta x and delta y that take me from x bar y bar to the intersection of the lines. Now the reason that we want to make the lines, the reason we want to approximate the functions as lines is because we can very easily solve for this delta x and delta y. This is a linear set of equations, and if I sub in the numbers here, I'm going to get 10, minus 1, 2, and 1. If I have a linear equation solving method, then I can find delta x and delta y. And of course the easiest way to do that is to say delta x and delta y is going to be the inverse of this coefficient matrix multiplied by the residual vector brought over to the other side, so minus 20 and 0. Okay, so I brought the residuals to the right hand side. I'm multiplying both sides of the equation by the inverse of this matrix, and I'm doing the same thing that you would do in the velocity and acceleration analysis in MATLAB. So if you punch that in the MATLAB, you're going to get these corrections delta x and delta y. They come out to be minus 1.67 and 3.33. And if you apply those to your initial guess, you end up moving over to x equals 3.33 and y equals 5 plus delta y 8.33. So that point, 3.33 and 8.33, that is this intersection point. So now if I start there and I do another step, alright, so I'll come over here and I'll do step 2. Let's see, my functions f1 of xy and f2 of xy are going to be equal to Okay, the residuals. So the first function was x squared minus y. The second function was 2 times x plus y minus 15. So that's the residuals. Now, plus the Jacobian matrix of the slopes, which in general is 2x minus 1, 2, and 1. So my Jacobian matrix at this step is going to be 2 times my new value of x, minus 1, 2, 1, times delta x and delta y. And the goal is to find a new delta x and delta y that drives this to 0. And that point, or that new delta x and delta y, will be the teeny tiny delta x and delta y that take me from this blue point over to the red point. So the red point is the intersection of those two functions approximated at lines if I start here and go up to the blue curve and draw another tangent line. Alright, so if I solve this for delta x and delta y, my residuals 2.76 and minus 0.01 plus the Jacobian matrix 6.66 minus 1, 2, and 1 times my deltas equals 0. Inverse of this coefficient matrix times minus of the residuals gives me delta x and delta y that are considerably smaller than before. I've got to go over another 0.3176, and I've got to go up by 0.6451, and if I do that, my new x will be the x I started with in step 2 plus my negative delta, 3.0124. My new y is going to be the y I started with in this step plus the 0.6451 delta, 8.9751. So it turns out that's very close to the actual solution in only 2 steps. If you do another step, then you're going to get close enough. Okay, so I just wanted to clarify exactly what the delta x's and delta y's mean. If we go back to the general algorithm, here's the general Taylor series approximation of a function. You toss out the higher order terms and you've got a linear approximation. Here it's in Q1 and Q2 instead of x and y. You write your vector of functions plus your Jacobian matrix times your deltas. You drive that to 0 by solving for the correct corrections, delta Q1 and delta Q2, which is the inverse of the Jacobian matrix multiplied by the residuals brought over to the other side of the equation. And then once you find those deltas, your new value of the unknowns is the initial guess plus the corrections. Then you repeat. Okay, so next I'll post a short video describing what this looks like in MATLAB.